Thank you, Fraser. And I'd like to also special thanks to the organizers for giving me an opportunity to introduce our research. So today, let me talk about slide ring materials and their applications. I'm a professor at the University of Tokyo. Let me start. This slide schematically shows the fracture of the chemical crosslinks. In the usual polymeric materials, long polymer chains are divided into short pieces with different lengths by fixed chemical junctions. On tensile deformation, tensile stress concentrates on the shorter chains because of heterogeneous lengths of network strands. So the stress concentration easily occurs to break down usual polymeric materials. To solve this problem, about 20 years ago, we invented novel network structure called slide ring materials by cross-linking the cyclic molecules of the polylactic. Then we formed a figure of 8 cross-linking junction which can move freely in the polymer network. So large deformation is realized keeping topology of polymer network in the slide ring materials. The most important feature of slide ring materials is a pulley effect. In this case, the figure of 8 junction can pass through the polymer chains freely to equalize the tension of the threading polymer chain, just like pulleys. We call this a pulley effect. So stress dispersion automatically occurs to toughen these polymeric materials. The other important point of the slide ring material is the entropy of rings. So this polylactic has two kinds of entropy because they have two components of ring and strings. So these polymer chain, axis polymer chain, can take a form of coiled conformation or stretched conformation. On the other hand, these ring molecules can form the aggregation or distribute sparsely, randomly in the polymer chain. So this polylactic has two kinds of entropy, entropy of rings and entropy of strings. But in the case of polylactic, these two kinds of entropy are almost independent of each other. But when they are cross-linked, the situation is drastically changed. So what is important in the slide ring materials? Not all cyclic molecules are cross-linked. There are many ring molecules remaining uncross-linked in the slide ring materials. These three rings are sparsely randomly distributed before deformation. And when you stretch the slide ring materials, in short time scales, polymer chain is change the conformation like this. And pulley effect starts to occur, and polymer chain can pass through the cross-linking point. But what is important here, these three rings cannot pass through the cross-linking point. So the pulley effect yields a heterogeneous distribution of free rings. So novel entropic elasticity emerges from the entropy of rings. This means that topological asymmetry of ring and strings is dynamic coupling between the conformational entropy of string and the distribution entropy of rings by the pulley effect in the slide ring materials. So the entropy bridges the gap between the nano and macro scales. So in polylactic is a very, very small nanoscale molecules. So the ring sliding motion, the force coming from the sliding motion is very, very small, in the order of piconewton or piconewton. But when we consider the entropy of rings, they produce a macroscopic force in the order of the megapascal or something like that. So this is very similar to the gasoline motion and bicycle pump. Next, let me show you some experimental results of the sliding motion of the cross-linking point. we measure the fracture behavior of the sliding gels. And generally, the fracture energy is given by the number of network strands in the unit area times the energy to cut the one network strand. This is called the Lake-Thomas theory. So many rubbers and gels, fracture behavior of the many rubbers and gels are well explained by this Lake-Thomas theory. This theory gives us a very simple relation. Fracture energy is proportional to the inverse root square of the cross-linking density. So you can see the usual chemical gel shows the fracture energy decreasing with increasing cross-linking density like this. However, sliding gel shows a quite different feature. You can see that fracture energy of sliding gel is almost independent of the Young's modulus, quite different from the usual chemical gels or rubbers. So this behavior is strongly dependent on how fast you stretch the sliding materials. At low strain rate, so sliding gel shows a much higher fracture energy than the usual chemical gels. But when you stretch very, very fast, so this behavior is quite similar to the usual chemical gels. This difference can be well explained by these cartoons. At low strain rate, this sphere-wet junction can move according to the macroscopic deformation. On the other hand, when you stretch the sliding gel very, very fast, this sliding motion cannot catch up with the macroscopic deformation, and this behaves as a fixed junction. So it became, it's very brittle, like the usual chemical gels. So this shows the strain rate dependence of the fracture energy of the sliding gels and the usual chemical gels. At low strain rate, so sliding gel shows a higher fracture energy than the usual chemical gels, but at higher strain rate, so the fracture energy decreased drastically down to the level of the chemical gels. So we can estimate the speed of sliding motion from this transitional strain rate, so to be on the order of the microsecond level. Recently, we directly measured the sliding motion by using the quasi-elastic neutron scattering technique. So, this sliding speed is almost the same as the value we estimated from the fracture energy measurement. Okay. So next, let me show you some applications of sliding materials. When we apply the sliding materials, we don't have to use only polyotaxane. We can cross-link the cyclic molecules in polyotaxane with various cheap polymeric materials. Then we can improve the mechanical properties of the polymeric materials without drastic change of the chemical properties and manufacture processes. Then we can apply the concept of the slide movable cross-links to wide area with low cost. These two movies are example of the improvement of the mechanical property in ionic gels. Okay. Sorry. So usual naiform gel is brittle like this. But when we add only 5 weight% of the polyotaxane as a cross-linker, mechanical property is changed drastically. You cannot cut this naiform gels with a polyotaxane with a cutter. This. And so some company, the Toyota Gosei, which is a group of Toyota Motor, has recently developed a direct actuator based on the sliding elastomer. Recently they released commercially Haptics, which is a sensor and actuator for the fingers. this haptics is used for the game machine in Japan. So the sliding elastomer has some advantage when they are used for the direct actuator. They have a very high director constant, around 10, because the cyclodextrin has a large dipole moment. And so Young's modulus is very, very small because of the Pulley effect. So, and it shows a very, very small hysteresis. And this actuator realizes high power, such as an actuator of 4 grams can lift up a weight of 100 grams as powerfully as human muscles. Now that this sliding material can be used as golf ball, surface of golf ball, and it was released recently. So the Hideki Matsuyama, is a Japanese golfer, is using this golf ball. Okay, next I'd like to show you the application of sliding materials to the polylactic acid. Okay. Polylactic acid is a bio-based and biodegradable polymers. It shows a high transparency and high Young's modulus. But the drawback is the brittleness. It shows a very small impact strength compared to polycarbonate. So to improve the mechanical property of the polylactic acid, we use polylactic. When we add a very small amount, about 5% of polylactic to the polylactic acid, elongation at break is improved up to the 30%, about 6 times of the neat polylactic acid. And the impact strength, isotope impact strength is improved about 7 times by addition of the polyotaxan to polylactic acid. So finally, I'd like to talk about the impact program, which is the largest national project for science and technology in Japan. The headquarters for science technology in Japan started impulsing paradigm change through disruptive technology program since 2014. This program ended this March for about 5 years project. They selected the 16 program managers, including me, and each program manager target is different. My target is to create a tough polymer, to create novel tough polymers for full body vehicles. Each program manager is allowed to use about $30 to $50 million budget to achieve the target. My budget is the largest of the all impact program, about $50 million. And also the company joining my program provides about $30 million by themselves. So the total budget is $80 million. So to achieve the target, I invited distinguished professors, Japanese professors in the field of the chemistry. So Professor Aida and Professor Harada, so joining to my project. And so they are researching the tough polymers and self-healing materials, and they provide the new concept of the chemistry to toughen the polymers. Okay. Then I invited other professors in the field of the polymer physics and polymer processing and the theory and simulation. And we are allowed to use one beamline of the synchrotron radiation facility about 300 days exclusively. Okay? And also we use a supercomputer a lot of time. But the main player in my program is not academia, it's a company. 5 major chemical company, Japanese company, joined my program to the project to create the novel tough polymers. Toray and Sumitomo Chemicals and Bridgestone and AGC, which is the largest glass company in the world, and Mitsubishi Chemical are the main player to create the tough polymers supported by the novel advanced chemistry by the academia. And Toray and Sumitomo Chemical created very, very tough polymers for the automobiles, such as structural resins and transfer resins. And Bridgestone's target is to reduce the thickness of tire about half by creating very, very tough polymers supported by the academia. And AGC and Mitsubishi Chemical is reducing the thickness of the separator and the membrane of the fuel cell battery and lithium-ion battery. And I'd like to show you some achievement by the companies. This Toray improves the mechanical property of polyamide resin by introducing the polylactic. So you know the hardness and the elongation at break has a trade-off relation. Sometimes they incorporate some small rubber spheres in the polyamide resin. Then the elongation at break is increased, but it became softer. But so Toray adapted the sliding materials, so they increased the elongation at break about 10 times at the same hardness. Okay. So this shows the bending durability test results. So usual polyamide resin shows bending about 2,020 times at break. But when they added only 5% of protection, bending durability is improved up to 19,000 times, about 45 times is improved. This shows the ion drop test. So usual polyamide resin is brittle like this. But when they add only 5% of protection, this polyamide resin is not collapsed like this. Okay. This protection works well for the composite. This is a usual polyamide resin with glass fibers. It's brittle like this. But new developed polyamide resin is not collapsed like this. Okay. And this is also effective for the CFRP, carbon fiber reinforced epoxy resins. So this bending number at break is improved about 3 times by using only 3% of protection. This CFRP is actually used for the Boeing aircraft. It's the highest level of CFRP by Toray. But new developed polyamide resin, developed CFRP composite shows much higher fatigue properties than the highest the CFRP they used for the aircraft. Finally, so our final goal is to construct a concept car using these materials, novel tough polymers. So I'd like to show you the. Okay. So about last September, we showed this concept car to the TV news. So many protection is used for the CFRP in this concept car. Yes, the weight of this concept car is about 850 kilograms. It's which is almost the half of the same size of the same size cars. And this car contains about 45% of plastics and 90% by weight and 90% by volume. So a usual car uses only the 10% of plastics by weight. So this car, concept car uses a lot of the plastics compared to the usual cars. And so the highest speed is now the 145 kilometers per hour. Incidentally, this car costs about $2 billion. And now our laboratory is now keeping this car. If you have a chance to come to Japan and visit my laboratory, so you can drive this car. So this is a summary of my talk. So about 4 years ago, I had a chance to make a presentation to the tough polymer to the Prime Minister Shinzo Abe and his main minister in his cabinet. And I asked him to join the experiment of the polymers, and he enjoyed a lot. And thanks to these successful achievement in impact program, Japanese government has made a decision to continue next impact program over 5 years, and prepared $1 billion budget very recently. So we are now considering next impact program. So we are now considering the microplastics problem for the next impact program. So I think the bio-based polymers and biodegradable polymer are not used so much because they are so brittle. So if the polylactic can improve the mechanical property, these bioplastics can be used in our daily life much more. So I think that it's a big challenge for the supermarket chemistry to solve this worldwide problem. Thank you for your attention.
Creative supermicrochemistry, materials chemistry, polymer chemistry, call it what you will. Amazing. Questions? Yes.
Is it possible to use waste polymer plastics?
Waste polymer plastics?
Is it possible to implement this sort of technique into waste polymer plastics? So, for example, like hard to recycle plastics.
Yes, I think yes, I think it can be used.
Because that could possibly tie in with your next impact.
It includes in such kind of recycling problem. Yes.
Okay, that's very powerful. Thank you.
Thank you.
Hi, thank you for a very wonderful talk. I'm very excited to see such a great application. So my question is about, for that kind of polymer, what about the air permeability? Since I found the material looks like rubber, and rubber is very widely used in the tire, in the automobile industry. So if your material is so great, and maybe used on the tires,
yes.
I'm concerned about that property.
In my impact program, so Bridgestone really developed a very, very tough tire. So I'd like to show the movies of that. But unfortunately, they don't use the polylactic in this case. They finally use the concept of the double network gel by Professor Gon. First, in my impact program, so every company used many ideas from the academia, and finally they select the most suitable one. It was not polylactic in this case. They finally used the concept of double network gel. The upper is the standard rubber, and the lower is the new rubbers. So you can see the crack does not propagate in the case of new rubbers. So the stress strain curve is almost the same, but crack propagation property is quite different. So then they can apply this rubber to the tire. Actually, my concept car uses this rubber, new rubber.
Thank you.
Thickness is about half, and the weight is about 60%.
Okay, great.
How quickly do the rings relax? Can you break the material if you pull too quickly?
Sorry.
So it takes some time for the sliding motion to happen. What if you deform your material really, really fast, like fast impact, like hit the car? Will it break or will it be elastic? Does the young modulus depend on the speed of deformation?
Yeah. I'm afraid so. I can understand your question perfectly. So, okay. I'd like to talk later. Okay. Answer. Sorry about that.
Very nice work. Can you say something about the temperature dependence of the mechanical properties of this polymer? Because I think they must be quite peculiar.
Yeah. Temperature dependence is important because I recently measured the sliding motion. Then the sliding motion is between the alpha cyclodextrin and the polyethylene glycol has a large temperature dependence. So I think at high temperature, sliding motion becomes fast.
Okay, I think that's it. So thanks for your
Thank you very much.